Here we want to do an underdamped problem. Okay, so I'm showing it in MATLAB, and we can see the motion here. And we want to come up with an equation of motion for this. And we want to also investigate how quickly this is dying off. So you can see the parameters that we have for this. They'll be copied down on the iPad screen in just a minute. Important thing is we're starting with an amplitude, but no velocity. Okay, so these are the easiest kind of problems, and this is what you need to do in the homework. Okay, so it's displaced by 25 centimeters initially with no initial velocity, and we allow it to go. And another important thing is that the damping is relatively low. Okay, so let's look at that again. We can see how it's dropping off, and we are going to try to figure out the equation of motion for this. All right, so let me switch screens. All right, so you can see I've copied down the parameters, and for the homework, you are just using Guy and Colley's equation. Now, the equation from Guy and Colley, it doesn't look like it's quite the full thing that we derived in our previous videos. It doesn't have the cosine part. Oh, and there should be a constant in front of this. Okay, let me actually put A for that could represent the amplitude according to Guy and Colley's equation. Okay, as we try to figure this thing out, it's less complicated than the full solution we have, which has its shortfalls. Okay, this is a perfectly good equation under a couple conditions. If V naught equals 0, because remember when we were doing harmonic oscillation with no damping, the cosine term was the only one that stuck around if V naught was 0. All right, so that's important that V naught is 0. And also if the damping, okay, is small. Okay, and by that, I mean that gamma is much less than omega naught. Okay, and I should have like a double much less than, not just that it's less than, but it's much less than omega naught, which we'll see in this case is a pretty good approximation. Okay, so first of all, when we're looking at one of these problems, and we saw it, so we knew that it was underdamped. But when you look at an oscillation problem with damping, you need to decide, is it underdamped or overdamped? So what we have to do is we have to look at B squared and look at 4mk and determine, we know this is underdamped, so we have to determine whether it's greater than or equal to 4mk. We already know that it's, greater than, less than, or equal to. And this case, we already know it's less than because of the graph, but let's show that that's the case. So if I take 0.5 squared, and I take 4 times 0.300 times 10, all right, it looks like the right-hand side is 40 times 0.3, that's 12, and this is going to be 0.25. So in fact, we can say it's more than less than, we can say it's much less than. Okay, so B squared is much less than 4mk. Therefore, our assumptions for the Guy and Colley solution are going to be pretty good. All right, so it should give us a very good answer, even though it's not going to be exactly right. All right, so to use the Guy and Colley solution, we need to know a couple of things. Okay, we need to first of all figure out the A value. Right. Well, to figure out the A value, we want to sub in what happens at time 0. Okay, and a few things that are important to remember when doing all of these equations is e to the 0 is 1. You need to know that cosine of 0 is also 1, but the sine of 0, this won't come into play in this problem, but it will in others. The sine of 0 is not 1, it is 0. Okay, so e to the 0 is 1, cosine of 0 is 1, and the sine of 0 is 0. That will be very important that you know those 3 facts. Okay, so at time equals 0, at t equals 0, x is x naught, and that will equal A e to the 0 times the cosine of 0. Okay, so that means x naught is a times 1 times 1. So a is x naught, which in this case is 0.25. So we now know what a is. All right. We also then need to figure out what omega and gamma are. Okay. Well, to figure out those things, okay, gamma is just b over 2m. We've defined it that way. So you just put in your numbers. So b was 0.5. And 2 is 2. And m is 0.300 kilograms. So when you put all of those numbers in, I believe you get 0.833. Okay. So we now have a gamma value. In order to get omega, we first need to get omega naught. All right. And so omega naught is the good old square root of k over m. Okay, so in this case, that's a square root, I believe that was 10 over 0.30. Okay, and so that comes out to be, I believe, 5.77. Okay, and that would be radians per second. By the way, the units on the decay constant, let's see, we're going to multiply that by time. It's just per second. So seconds to the -1. All right. Now we need to figure out what omega square or what omega is. And we probably a better way to say the equation that for omega is that omega squared is omega naught squared minus gamma squared, and then take the square root. So omega is the square root of that. I just like saying it the other way because there's more symmetry there. It just looks nicer. But then to actually get omega, we'll have to take the square root. Okay, and when we put in the numbers that we just got, there's a square root of 5.77 squared minus 0.833 squared. Okay, and we end up with 5.71. Okay, and that would be in radians per second. Okay, so you can see that's not that different from omega naught, which is why the Guy-Kali solution will be sufficient. Okay, so now we just have to fill it all in. So x is equal to the amplitude, 0.25 meters, okay, times e to the negative. Actually, I'll leave the units off. We'll just say that the x in meters with t in seconds will be 0.25 e to the negative gamma 0.833 times the time times the cosine of omega t, so 5.71 t. Okay, and this gives us the equation of motion that we just had, very close to it. There is a sine term, but it's going to be a smaller term, and it won't have much impact in this case because of the low damping. All right. Now, another thing that we said we might want to find is how quickly is this dying off? Okay. So if I wanted to find what it's doing one cycle later, I would need to find the period. Okay. The period is 2 pi over omega. Okay. So if we look at that, okay, because there are 2 pi radians per cycle, and omega is the radians per second. Okay, so that will give me the seconds of time, and it's about 1.10 seconds. Okay. Now, if I want to find the height then at that time, I just take my formula for x and I put in the numbers. Okay. And actually, if I'm doing exactly one period later, okay, the cosine part of that shouldn't matter. Okay, we just need to figure out how much the amplitude drops off one period later, and that's the decay part of this. So it's 0.25 e to the negative 0.833 times the period. 1.10 seconds, okay? And we'll be at 2 pi for the cosine part because it's a cycle later. So when I put those numbers in, I get that the amplitude is all the way down, 1 period later is down to 0.10 meters. Okay, so remember it started at 25 centimeters as the amplitude, and one cycle later, we're down to about 10 centimeters instead of 25. And so that's how you go about doing one of those problems. If we were trying to find it at a time that wasn't a period later, then we would have to use the cosine part. But every time we get 1 period later, the cosine is back up to a value of 1. So, all right, we'll then in a moment look at the underdamped case. Okay, I believe I said we'd look at the underdamped case. I meant the overdamped case. So let's look at that now. So I kept everything the same, except I increased the damping to a damping constant up to 5. So you can see there's no oscillation at all. It just dies down. All right. So we can figure out the solution in this case. Okay, so you'll notice there's a couple interesting things. It's not quite an exponential decay curve because there's this little beginning bump. It sort of starts out flat out. By the way, there's no initial velocity again. And then it begins to sort of follow more of an exponential decay pattern. So let's switch over to the iPad and look at the solution. Okay. Okay, so here we have the parameters, and remember our general solution for overdamping is right there, okay? So in order to figure this out, we'll first need to figure out what R1 and R2 are in terms of numbers, and then we're gonna have to figure out C1 and C2, which is a little more complicated than what we did in the last problem, okay? So R1, if you remember, R in general, well, actually, I'll just write out R1 was negative B, okay, plus or minus the square root of B, well, that's in general, B squared minus 4mk all over 2m. I put plus or minus, so that is not R1. That R1 would just be the plus, okay, and R2 will just be the minus. Minus the square root of b squared minus 4mk all over 2m. For the sake of efficiency in this video, I'm just going to give you those values. So R1 ends up being negative 2.32. You can just sub the numbers from the parameters at the left. And R2 ends up being negative 14.3. Okay, now this is interesting to pause and note. So x is C1 e to the negative 2.32t plus C2 e to the negative 14.3t. If you know much about exponential decay, this decay is tremendously fast compared to the other decay. All right, so the second term is why we don't have a true exponential decay curve, okay? This is what causes it to sort of, when it started out, it was sort of flat for a moment, and then it went into the exponential decay. But this dies quickly, which explains why the graph quickly goes into something that does look like a true exponential decay curve, that this one is like kind of determining the decay. If we completely ignored the second term, we wouldn't be that far off. Although the initial behavior, the stuff that's happening kind of in this original part, the initial part would be far off. But once we get a little bit of time out, the C2 term will just not matter much at all. Okay. That being said, let's go ahead and finish getting the solution. Okay. So this time we have a C1 and a C2 that are unknown. Okay. So we can do what we did before, which is we can substitute at time 0 that x equals x naught. So x equals x naught when t equals 0. And if we put that in, we know that x naught in this case is 0.25 is equal to C1 e to the 0 at time 0 plus C2 e to the 0 as well. At the initial time, those will both be 1s. And so 0.25 has to be the sum of the coefficients. Now, obviously, that doesn't give me the coefficients, just gives me an equation that I can use that has 2 unknowns. To get a second equation, I actually need to take the derivative of x. So let me do that here. We need to find x prime, or x dot in the case of physics here, okay? So what will x dot be? Using the chain rule, x dot will be negative 2.32 C1 e to the negative 2.32t minus 14.3 C2 e to the negative 14.3t. All right. And now what we can do is we can put in that V naught equals 0 when t is 0. Okay. So 0 is equal to negative 2.32 C1 e to the 0 minus 14.3 C2 e to the 0. Those e to the 0s all become 1s. So we end up with 0 is equal to negative 2.32 C1 minus 14.3 C2. We can make that all positive and say this is 2.32 C1 minus 14.3 or plus 14.3 C2. Get rid of the negatives. Usually we make fewer errors when we do that. All right. And then we have 2 equations with the same 2 unknowns. So that equation and this equation can be solved for C1 and C2, right? Now, when you do substitution, you usually take the simpler equation and substitute it into the more complicated one. Okay, so when we do that, we'll have, I tend to like to get rid of C2. I can say that C2 is equal to 0.25 minus C1. Sub that over. So 0 is equal to 2.32 C1. Okay, plus 14.3 times 0.25 minus C1. Okay, distribute. Okay, and you can get 0 is equal to 2.32 C1. Let me just real quickly get a number here for 0.25 times 14.3. I forgot to pre-calculate that. So it looks like plus 3.57 times, I'm sorry, minus 14.3 C1. Okay, and 14.3 minus 2.32. So this gives us, if we bring those C1s to the other side, we'll get a total of 11.98. C1 is equal to 3.57. And so C1 ends up being 0.298. Okay, and then you just sub that back over. C2 is a quarter minus that. So C2 ends up being negative, notice, negative 0.0483. Okay, so that's nice because we can now we have the constants, and so we can now write out the equation of motion. Okay, so the stretch of the spring will be x equals C1, which is 0.298, okay, times e to the, oh, what was that exponent? Negative 2.32 e, okay, minus 0.0483, okay, e to the, that was negative 14.3 t. Okay, and just of note, this, because this is negative, that's what actually causes this to be the kind of the second term fights the decay for a short period of time until it dies off, which is why the decay doesn't really start immediately. So that's just of interest to explain why it does what it does. Oh, and probably to be consistent, I should, you know, maybe put that coefficient in parentheses, or yeah, probably not a bad idea to put both of those in parentheses. So this problem you had to attack by using the position and its derivative and the initial conditions. Okay, so quick review. We used that the position was x naught when t naught was 0 to get one equation for C1 and C2. And then we had to take the derivative. So we came over here and we had to take the derivative in order to use that V naught was 0 when t equals 0. We needed an expression that would allow us to set V naught equal to 0. So that required taking a derivative. All right, and then that gave us two sets of equations to solve for two unknowns. So that's how you do an overdamped problem.